In this example, we have a rocket that's traveling straight up at 80 meters per second. Then it runs out of fuel at a height of 7,000 meters above the ground. We want to determine the maximum height that the rocket reaches and the time that it will take before it falls back down to the ground. And we're going to neglect the effects of air resistance. All right, so what do we know? We know that initially the rocket is traveling at 80 meters per second, and we'll define that as our time 0. That height that the rocket is when it runs out of fuel is 7,000 meters, and that there's no air resistance. This is important because that tells us that the acceleration of the rocket, which is just falling at that point, is constant and equal to minus g. All right, we want to find the maximum height that the rocket reaches and the time it takes for it to fall back down to the ground. All right, so let's get familiar with the problem. So to get familiar with the problem, the best way to do that is to draw a figure. Draw it and label it. This is the best way. All right, after we have the figure, then we're going to determine which of the basic equations will be the easiest to use. And to determine that, we need to specify, well, what do we know and what do we want to find? All right, so this is what we know. We know the initial velocity. So here's the rocket. Initially, it has a velocity of 80 meters per second at a height of 7,000 meters. It runs out of fuel, so its momentum will take it up a bit, and then it will turn back around and fall back down to the ground. So the maximum height I'm going to label as the apex, and we have the acceleration of gravity, and I've defined where my 0 is. So here's my origin right here. Now, even though I'm using the xy coordinate, this is really just a rectilinear motion problem. It goes up, it goes down. All right, so beyond what the problem gave us, what else do we know? So if you look, what happens when the rocket slowly slows down and then loses all of its velocity and then turns back around? The velocity at the apex is going to be 0. So that's what else we know. All right, well, what do we want to find? We want to find the maximum height, so the height at the apex, and the time that it takes for the rocket to go all the way back down to the ground. All right, well, the equations that we can use are the constant acceleration equations, right? Because we know there's no air resistance. So these are the 3 equations that we can choose from. Now, which is going to be the easiest? So let's say that we want to find the height at the apex. All right, well, we want to find height. So the equation should have height in it. All right, so this first equation won't do. It doesn't have height. All right, the second equation has height, which is represented by the s, but it also has time. And at this point, we don't really know the time that it's going to take for it to get to the apex. All right, so the third equation has velocity, which we know, acceleration, which we know, and the height, which is what we want to find. So we're going to use this one to find the height at the apex. All right, what about the final time? All right, so after we find the height at the apex, we know the heights. And we know that that is the height that we solve for, and we know also that when the rocket comes back down to the ground, the height is 0, because that's where I've set my 0. All right, well, the first equation, we could use it, but we don't know the velocity at the ground. We could use it as an intermediate step to get the time at the apex, but we don't really want to know that. So that equation won't work for us. The second equation has height, has the initial velocity, has time, which we want to find, and the acceleration, which we know. So this is the equation that we're going to use to find the final time. All right, maximum height. we use the equation that we picked out, and we just substitute the variables that make sense according to our figure. So the velocity at the apex minus g, height at the apex, original height, original velocity. And then we can substitute all the numbers in, right? The velocity at apex is 0, and then we can solve. So it's easy. The hard part is picking the right equation. All right, the time. All right, we'll use the equation that we chose for the time, substitute the variables in it that make sense for this problem. The height at the final, right, which is defined here at the ground, is 0. Height initial, 7,000, and so on. So we just plug in what we know, and we get the time.